Hello and welcome back to CS210. This is the third installation for Module 2 where we will discuss about different ways of solving recurrences or getting the closed form of recurrence relations. So, as an overview, we're done with the partition tree method and the backward substitution. In this lecture, we will discuss about forward substitution, converting to a sum, and the master theorem. Recall that a recurrence or a recurrence relation defines an infinite sequence by describing how to calculate the nth element of a sequence given the values of smaller elements. As in, we were able to define the definition of something with respect to itself by defining by using a smaller instance. So, by smaller instance, ibig sabihin mas maliit na yung pinapasok natin na input. So, in principle, such a relation allows us to calculate t by n for any n by applying the first equation until we reach the base case. So, to solve a recurrence, we will find a formula that calculates t of n directly from n without using this recursive computation. And note that not all recurrences are solvable exactly, but in most of the cases that arises in analyzing recursive algorithms, we can usually get at least asymptotic or big data solution. Okay, so the first method that we will introduce in this lecture is called the forward substitution. There are two steps for this. The first one is the guessing part, and the second one is the verifying part. Okay, so the first part for guessing is to perform some small cases starting from the base case n equal to 0 and try to define n equal to 1 using the base case and so on. Okay, so if we have a table such as this one, we have n equal to something and the evaluation of n, we can somehow guess that the function behind n and the corresponding t of n is n squared. So once we have a guess, then we will use the mathematical induction to verify if our guess is actually correct. So just to recall, the process of mathematical induction needs a base case and the corresponding guess. So for base case, let's try to use our evaluation for t of n, and we will use n equal to 0. So our t of 0 is equal to 0 squared. So for the base case, we're done. For the induction hypothesis, we will assume that for n minus 1, this condition holds. And by assuming that this is correct, we will arrive to our guess, which is we will arrive to t of n is equal to n squared by assuming that this is correct. So we can do this by performing the following operation. So we have t of n equal to this one, which is the original recurrence formula. Okay? So since we have this induction hypothesis, we can simply replace t of n minus 1 by our guess. Okay? So by manipulating this, wala na tayong something of the form t of something sa formula. Can simplify this expression by doing some algebraic manipulation. If we assume that this is correct, and we replace this by the original recurrence formula, and we arrive doon sa final guess natin, then we're done. The second method that we will introduce is by converting a recurrence relation to a corresponding summation. So we are only interested in these three types of recurrence relation form. The first one is when we have a recurrence relation na ang size of the input is n minus 1 plus some function. The second one is if meron tayong constant a na minumultiply sa t of n minus 1 plus some generic function ulit. And the last one is when we have some constant a times t of n divided by b. Okay? So, these types of recurrence relation is actually obtained from some algorithms na ang ginagawa is decrease by 1, then conquer, or divide and conquer type of algorithms. So, merge sort, for example, will fall under this case kasi we have 2 times t of n over 2. So, we have a equal to 2 and b equal to 2. Okay, so if your recurrence relation is of this form, then you can use this method. For this method, your idea is that the recurrence relation can be converted to a summation form, and then from the summation, we can compute for the closed form, similar to the method we used for non-recursive algorithms. So let's start with the first form. If this is the form, we can transform this recurrence formula to something like this. And then we have summation from I from 1 to n of the function of I. So for example, if our recursive relation is this one, so t of n is equal to t of n minus 1, and our function is n squared, and then we have a base case of t of 0 is 0, we can immediately have a summation form na equivalent to summation of I from 1 to n ng f of I. So, in this case, we have I squared plus t of 0 na equals to 0. So, we can simply ignore this part. Pagkatapos nun, we can just simply treat this as something na kailangan ng closed form. Okay? So, we have a lot of tools that we can use to get the closed form of these kinds of formula. Okay? That's for the first form. The second form is if we have a multiplier for the t of n minus 1. Okay? So if we have something like this, it's just a matter of replacing the content. So t of n is equal to summation of something. Instead of I, we have n minus I, and a raised to I plus a raised to n. So let's have an example para mas visible sa atin. No? We have a equal to 2 and we have f of n equal to n. Okay? So for the corresponding summation, we have I equal to 0 to n minus 1, and then our function is n, so we have n minus I. We have a equal to 2, so we have a raised to I, so that's 2 raised to I, plus 2 raised to n times the evaluation of the base case. Okay? The last form is the recurrence relation obtained from divide and conquer algorithms. So for this form, we know that the divide and conquer have 2 as A and B na equal din sa 2. And our f of n is the running time for merge. We have n. So, by replacing the values for a, b, and f of n, we have this form. Ito ay n minus 1, no? Madali lang siyang ma-simplify because a and b is equal to 2. So, for this part, makakancel si 2 to the I, and we're left with this one, with this expression. And then 2 log of n base 2, makakancel itong part na to, bababa si n. So we have n times the evaluation of the base case. Yung evaluation of the base case is actually parang theta of 1 or constant time. But if we will follow yung basic operation, count of basic operation na key comparison for the base case, wala namang key comparison involved in the base case. So we have an evaluation of 0 here. So the running time of the merge sort based from this conversion to summation is actually equal to n log n, which is consistent dun sa previous methods. The last topic is about the master theorem, and this tries to summarize what we can deduce from the closed form of the recursive relation based only from A, B, and f of n. So the master theorem can be applied to divide and conquer types of problem. Yung mga tinatry niyang i-divide yung size of the original input size to uh, B components. P of n has the following asymptotic bound. So we have three cases. For this, hindi tayo nakakakuha ng exact count for the basic operation execution, but we obtain an actual asymptotic notation in theta. So wala nang in O or in omega, but in theta, which is good, no? For getting a better approximation of the running time. The first case is when we can show that our f of n obtained from the recurrence relation is in O of n raised to log of a base b minus for some epsilon na constant greater than 0. The second case is when we can prove that f of n is in theta of this evaluation. And the last case is when we can prove that f of n is in omega of this. So using the value of a, b, and f of n, we can evaluate this form and see whether ano yung relationship of yung evaluation na to with respect to our f of n. And then we can deduce which one is the case. Let's have an example, no, for the master theorem. For example 1, is relatively easy. We have a equal to 9, we have b equal to 3, and we have f of n equal to n. So we are comparing our f of n to n raised to something, and yung something na yon is log of 9 base 3. This is in theta of n squared. And we can also say that f of n is actually in O of n squared, okay, for some epsilon na equals to 1. So, using the master theorem, the running time of this algorithm is in theta of n squared. For the second example, we have 1 na A, and we have 3 over 2 as B. Okay? Our f of n here is a constant equal to 1. So we're comparing 1 and the evaluation of this form. And this is equivalent also to 1. Since this is in theta of 1, then case 2 yung mag-a-apply for the master theorem. And so, this is in theta of log of n. Okay, so that's for second case. I will leave the example 3 and 4 for your analysis. Okay, so in summary, we presented several methods to solve recurrences. Um, for master theorem, it is a requirement that you can extract values for a, b, and f of n. For the recursive relation of this form, we can convert it to a sum. However, if hindi siya magpo-fall under this pattern or this form, then we can always use partition tree, backward substitution, and forward substitution.